So when we're differentiating trig functions, the first thing that we need to remember and acknowledge is that the derivative of sine x is cos x, and the derivative of cosine of x is negative sine of x. So they're the two things that we definitely need to remember before we even start these questions. The other thing that we need to remember is the product rule, the quotient rule, and the chain rule all still apply, even if there's a trig function involved. So our first example is just a simple, straightforward, normal differentiation techniques. So we've got x squared plus sine of x, and we need to do the derivative. So dy by dx, the derivative of x squared is 2x, and then the derivative of sine of x is cosine of x. And we just treat each part as its own, just like we would a normal function like x cubed plus x squared. So that's the first one. The second one is a little bit different. It's almost like it's a product rule type question. So we've got 5 sine of x as our function, and when we do the derivative, let's treat it like a product rule. So we're doing the derivative of the first, which is 0, because the first is 5. So 0 times sine of x, and then add the derivative of the second, so the derivative of sine x is cosine x, multiplied by the first. Okay, 0 times sine of x disappears, so we would just end up with 5 cosine of x as our answer. This next one is a bit more of an obvious product rule type question, because you've clearly got one function multiplied by another function. So when we do the derivative of the first, so the derivative of the first, we're looking at the derivative of negative cosine x is going to be positive sine x multiplied by the second. Add the derivative of the second, so we're just looking at the derivative of sine of x because the 1 will disappear, which is cosine of x, multiplied by the first. And then we can expand. So we'd have sine x plus sine squared x plus 2 cos x take cos squared x. Okay, and that's simply just from expanding our normal brackets. So the next example is a quotient rule question, because we've got one function divided by the other. So we have to remember our rule. So it's bottom d top minus top d bottom all over the bottom squared. So we've got dy by dx is equal to bottom d top minus top d bottom, okay, all over the bottom squared. So you can see there I did the bottom function, which is cosine of x, multiplied by the derivative of the top, and the derivative of sine of x is equal to cosine of x, and then we do minus the top times the derivative of the bottom, and the derivative of cosine of x is negative sine of x. Then we can expand the brackets, so we'd have cos squared x plus sine squared x over cos squared x. And if you remember, the Pythagorean identity is cosine squared x plus sine squared x equals 1. So that means the top part of our fraction here is 1, and we get 1 over cosine squared x. Now, just as a bit of a recap, so sine of x over cosine of x from our unit circle is actually equal to tan of x. So I'm just going to do this in green. This actually equals tan of x. So it means that our derivative of tan x is equal to 1 over cosine squared x. So if you ever have a tan function, so a trigonometric function of tan, you would know that the derivative of tan x is 1 on cos squared x, if you had any like that. The next lot of examples are chain rule. So we've got this first one. If u equals 2x plus 1, determine the derivative of sine of 2x plus 1 using the chain rule. So to start with, I generally write down our u function, which is 2x plus 1, and we do du by dx, which is 2. And then we've got y equals sine of u. And then we do dy by du, which gives us cos of u. Because remember, the derivative of sine is cosine. Then to get dy by dx, we multiply those two things together. So we would do 2 lots of cosine of u, and u is 2x plus 1, so we end up with 2 cosine of 2x plus 1 as our derivative there. Again, remember, we just substitute that u value back in and we can get our answer that way. So that was a stepped out chain rule question. Then we've got one like this, and some of my students call it the number bracket rule, but it's the adaptation of the chain rule where we bring the power to the front and then we multiply it by the derivative. So when we do this one, we're going to have dy by dx equals, and we're going to bring that power down to the front, so we would have 4 at the front, and we reduce that power by 1, and then we multiply by the derivative. So the derivative of sine of x is cosine of x. Then all we would have is 4 sine cubed x cos x. And that's our derivative there. The next one is a chain rule question again, but we're going to just use our knowledge, instead of having to do it as dy by du and du by dx and doing it like that, we're just going to use our knowledge of how to do that with going straight into doing dy by dx. So we would do, what is the derivative of cosine? So the derivative of cosine is negative sine. And then we're going to have 2x plus 3. And then we have to multiply it by the derivative of the inside of the bracket. So our derivative of 2x plus 3 is 2. And then we just bring that 2 to the front, so we would end up with negative 2 sine of 2x plus 3. So all I did there was I thought about what's the derivative of cosine, and then I wrote that in with the u function there, and then I had to think about what's that derivative of that inside function, and we multiply it by that to get our answer. And the last example is the same sort of question. So we work out what's the derivative of sine. So the derivative of sine is cosine, and then we would have cosine of 5 take 2x, and then we have to multiply it by the inside of that bracket, the derivative of the inside of the bracket. So 5 take away 2x, the derivative is negative 2. So then we would just bring that to the front, and it's negative 2 cosine of 5 take 2x. And that's our derivative. So hopefully this has helped give you a bit of an understanding about doing differentiation of trigonometric functions. Just remember, if you do any of these on your calculators, sometimes it gives you a different looking answer that is still correct. So just be aware of that. If you are checking answers on your Casios, they do give you a different answer. It might look a little bit different, but it's the same thing.